Hello everyone, I am Yusuf and I am here to explain you optics experiment for your course Optics for Engineers. Today I'll talk about experiment 1, which is detection of light. The purpose of this experiment is to get familiar with the different optical components which we are going to use in our experimental procedure. Next, we will try to measure the light quantitatively from helium neon laser. And lastly, we will see how light can be manipulated using different optical components introduced in the optical path. This lab 1 is divided into four subsections. First, we will see the calibration of neutral density filter. Next, we will calibrate the beam splitters, which is also a kind of optical component. Then we will try to measure photodiode voltage using oscilloscope. And lastly, we will calibrate the photodiode also. Let's start our first subsection, calibrating neutral density filter. For this experiment, we need three optical devices. First, it's a helium neon uh, laser beam, and then we need OD3 density filter, and then we have an optical power meter. Before starting our experiment, we need a safety precautions for our eyes. Now let's start. First, we will turn on the power, and then we will press the ATT button, which will calibrate this OD3 filter. After that, we will press the lambda button, which is to, calibrate the power of this laser beam, which is same 633. Now we will save this wavelength, and now it shows the power of this helium neon laser beam without any neutral density filter in place. Now we will introduce the ND filters and with different optical density, and we will see the how with the change in the optical density our laser beam power changes. So this is the filter wheel, which has a different optical density glasses, as you can see in the circle. And if we change the we introduces the optical density of 0.2. As you can see, the power is keep on decreasing because the optical density filter reduces the intensity of laser beam that can be shown in the power meter. So again, if I try to change the optical density, the power reflect is like keep on decreasing. So now we'll go for 0.4 optical density. See, the power keep on decreasing. So likewise, as we increase the optical density, it will like block the transmittance of the laser beam, and this can be reflected on the optical power meter. So far, we calculate the power of the laser beam using ND filters with a varying optical density. We can measure the optical density of different ND filters using the spreadsheet, or you can use with the simple OD formula, which is the log of the reciprocal of transmittance, like meaning the incoming light from the laser beams is is hitting this ND filter, how much of the light passing to the power meter. So that's it, how you can calculate the optical densities of these ND filters. Okay. Now we will introduce a beam splitter, a cubic beam splitter in the optical path, and as you can see, this beam splitter divides the optical light into two output. One is in the towards the detector and the other is towards me. So we will try to measure both this output and see how effectively it distributes the beam into two different paths. So first we will try to measure output 1. As you can see, the output 1 is of this numerical value, and now we are trying to measure the output 2.
Yes, it's a line.
So you can see it shows the different numerical value. Now we will calculate the ratio of it. The ratio defines how effectively this beam splitter splits the beam into two different optical paths. Now we will demonstrate the planar beam splitter, which can split also the light into two different directions. So first you can see there is a it directs the light in the straight direction and also towards me. So we need to measure the both output and find out the ratio of it, how effectively it distributes the light into two directions. So first we can see in the straight direction it shows this numerical value. Now we'll try to see the output 2 for this planar beam splitter. As you can see, it shows this numerical value. Now we'll try to find out the ratio of it, and this ratio will tell us how much light is being splitted by this optical device, which is planar beam splitter. Let's move to the third section of our experiment, measuring the photodiode voltage using oscilloscope. Here we have an optical component, photodiode. It is a device that converts the light into electrical current, and here the amplitude is set to be 20 decibel to boost the signal to the oscilloscope. And we have an oscilloscope. This is an electronic instrument that displays voltage waveform and allows for various measurement on the software. And this is connected with a BNC cable, which is just an electronic cable that connects the device to the computer. The functionality involves the photodiode is positioned to face the ceiling light, capturing the ambient light, and this output is sent to the oscilloscope for further manipulation to the software. Now you can see by capturing the ambient light by this photodiode, the signal is shown on this software. And if we just block the intensity of the light to ambient light to this photodetector, the signal changes. That means it precisely captures the ambient light and shows in the form of waveform on this software. And calibrating the photodiode. First we will see the minimizing background room light. In this we need two components, which is chopping wheel and lock-in amplifier. Chopping wheel is an optical device that periodically interrupts or modulates the light beam, creating a pulsating light signal. And lock-in amplifier is just an electronic instrument that detects and amplifies signals with a specific frequency, effectively filtering out steady background light. The purpose of this to ensure accurate calibration by eliminating interference from ambient light. The functioning, includes the chopping wheel modulates the light hitting the photodiode, and locking amplifier detects this specific frequency, ensuring only the desired signal from the laser is measured by the detector. Now we'll develop a calibration curve for the photodiode, which includes uh, to relate the photodiode input voltage to the power of incident light. And this can be done by placing the neutral density filter wheel and chopper wheel between the beam splitter and the photodiode measurement and taken for each ND filter. These measurements combined with previous calibration are used to calculate the power incident and on the photodiode. A plot is then made to visualize relationship between the photodiode voltage and the incident light's power. Okay, cut it. Start. Okay. Now we will see the adjust the phase between chopper and photodiode signal. For this, the components include the chopper control, computer oscilloscope, and the optical chopper control. The purpose of it is to synchronize the signal from the chopper and the photodiode, and this is done through by connecting the chopper and photodiode to the oscilloscope and adjusting the chopper position. The two signals are made to overlap, ensuring the accurate measurements. So after mounting and optimizing the photodiode position, we will adjust the phase between chopper and photodiode signal. The purpose of it to synchronize the signal from the chopper and the photodiode. Then we develop a calibration curve of the photodiode to relate the photodiode output voltage to the power of incident light, and then we will determine the linearity of the photodiode to check the photodiode operates linearly with respect to the incident light or not. So in simple terms, this section focus on calibrating the photodiode to ensure accurate light intensity measurement. The calibration involves minimizing background light interference, optimizing the photodiode position, synchronizing signals, and developing a calibration curve and assessing the photodiode's linearity. This can be done to proper calibrate the equipment, ensures that the photodiode provides accurate reading across various light intensities.